mentioned, we are presenting you the active learning paradigm from the HumAIne European project, and the active learning paradigm is one of the human AI collaboration paradigms that we have in HumAIne project. This presentation, the first part will be done by me. I'm Clement Kenda from Joseph Stefan Institute, and then we will have the second part, which will be done by the company GFT. It will be about the implementation of active learning methodology in a particular pilot case, concretely a smart ticketing pilot case within the project. So the agenda for this first part, we will go into the details of active learning in the beginning, introduce how it works in general. Then we will go into the sampling strategies. We will check how we implemented this in HumAIne project. And then I will also show you a little bit of use cases that we have within the HumAIne project. So basically, active learning could be described with what we see here on this slide, and it's about making machines smarter with less data. We all know that the core of the, let's say, data science and building machine learning models is the availability and the quantity of the data that we have. So generally speaking, the more data that we have, the more useful data that we have, the better model we can build. But it's not always necessary to use all the data that we have available, especially if acquiring this data or acquiring labels of this data is expensive. But we can be more, let's say, smart about it and only use the data that really brings us value. So getting value out of the data is briefly described in the scheme that you see on this slide. And this picture depicts the so-called cross-industry standard process for data mining, or shorter CRISP-DM. This is a quite old methodology, I would say, but it's still very much valid today. So it is basically a cyclical process through which you build and improve the implementation of machine learning or AI components for your business or for your problem. So it all started in this beginning part here, which is business understanding. So it means that we need to be aware of what are our problems, what are our pains, and we need to have some intuition how we could use the data and data mining processes or machine learning models to improve these pains that we have. So the first, we need to somehow understand what we are dealing with, and iteratively through this scheme, we might be able to also improve this understanding. So once we know what we want to do, we want to look at the data. So the data that we have available pretty much in majority of, let's say, pilots through the manufacturing industry or through other similar consumers of these services is very messy. It's not really understandable what's the origin of this data. Some of this data can be, I don't know, even in some paper sheets and so on and so forth. So it's really important to understand where this data is, how we can bring this data together, and finally, when we have the data together, which part of this data to use and in what way. So basically to understand if, let's say, we bring all the data together, let's say simplified in an Excel table, to understand what each column of this table says. And even furthermore, this data cannot be all useful because it can be, it can have issues, it can have biases, it cannot be clean, it can have missing values and so forth. So we start this second phase, which is data, with the third phase in this diagram, which is data preparation. This is basically, together with the modeling, the most time-consuming part of every machine learning solution that we are trying to build, because dealing with the data, dealing with the missing values, with noise, and whatever is in there takes usually up to 80% of the time that we spend in this whole process. And this is very tiresome business, which of course, with new methodologies that we are facing in last years, is becoming faster still. Okay, data preparation means the following. So we select what data we will use. We select what kind of thing we will predict from our data. So in these concrete cases, when we are dealing with active learning, this is a, let's say, subset of so-called supervised machine learning. And supervised machine learning basically takes a description of the system, which we call the feature vector, and then it predicts the state of the system, which we call a label. So typically, if today we will talk about the smart ticketing use case, where a ticket is basically a piece of text that a user sends to an IT help desk system. We would like to extract out of this data, for example, to which team in our organization we need to send our ticket. So the description, the text itself, we will use it to build the feature vector, and the team where this will be sent will be the so-called label. So when we get this raw text, of course, we cannot directly use it for machine learning. We need to do something with it. Either we calculate some TF-IDF weights out of it, or we create an embedding out of it, or we search for a particular word. It depends on our use case. So the data is not only textual, for example, we might also have some categories that the user has filled in. We might also have some numerical values and so on and so forth. So somehow we need to bring all of this to the same level, let's say, to build a so-called feature vector. And feature vector typically is a vector of numerical values. And once we have this prepared, we might also do something that's called feature selection. So not all columns in our data will give us useful information. So maybe the ones that are not useful, we will try to reduce already in the beginning. And we will, of course, take care about the stuff that we find out about our data in the beginning. So what to do with the missing values, what to do with the wrong values, what to do with data that is maybe not in the correct format, and so on and so forth. So once we are dealing with this, we do the modeling part, which is, I guess, the nicest part of the machine learning process. And then we iterate this. Of course, already in this phase, we try to tweak the feature vectors. We try to add additional features into our data. Sometimes we also try to bring out external sources into our system, like I don't know, information about the companies, information about the system, or whatever we could find that could be useful. And then we try to improve these models. Once this is done, we evaluate this model not only from the perspective of a data scientist, but from the perspective of business understanding. So here we are now at the bottom of this scheme. If the model is good enough, we will deploy it, right? So it will bring some additional value to our business. But at the same time, or if it's not good enough, we want to reiterate. So we go back to business understanding and trying to improve this whole thing, because iteratively we get more and more insight into our problems. All right. So when dealing with machine learning, there we have the data challenge, which means that we need a lot of labeled data, and sometimes this is really expensive, because at the end, usually a human needs to sit in front of this data. Either this is a text, a picture, or some numerical data, some curve, and he or she needs to decide what this data represents, and it needs to be labeled. So for example, if I give you like one example from HumAIne, where we are dealing with medical records, a doctor needs to look at these medical records, take all this information into account, and then extract the features that we want to for our model. And the laborer himself or herself is like really expensive, and moreover, they don't have enough time to just label all the data that is available. Okay, and we have established that this is an expensive task, and the important intuition behind this is that not all the data that we have contributes equally to the learning process. So the active learning is all about this smarter approach, where we select data from our data set that is really informative, and it will contribute the most to our learning process, to our model. So here in this picture, we see that basically active learning is a loop. It's something that's being repeated. But it starts somewhere, and it starts here at the append phase, where in the beginning we have a very small labeled data set, which I will talk a little bit later how we prepare it. Once we have this model is now able to give us some more insight into the other data. So we have this data, we build the model, and then we put this model through all the other data that we have in the data set, and we see what the results were. And these results will typically help us to select a particular example out of this data for which we expect that will give us the most information. So the whole idea of active learning could be to use fewer examples that need to be labeled and to come up with the same model as we would if we would label all the examples. So here we go a little bit into the detail. So this diagram shows you that we start with this initial training data set. We build a simple model, but we also have in the background a large data set of unlabeled data. So basically in smart ticketing use case, we have a big database of these particular tickets, but we don't know much about these tickets. So for example, we don't know to which team they should be directed. Okay, and here we employ now the active learning process. Basically, we ask ourselves, do we need more training data to improve our model? So basically this question can be paraphrased if our model is already good enough. If we don't need any more data, it means that our model is good enough and we can terminate the cycle. But usually we do need more data. So we use now the model in the current state that we have to do the prediction on unlabeled data set. This model will give us labels for all the unlabeled data. They will be uncertain, of course, but it will also give us an estimate how the model is certain that the data that we have so that the prediction that we have are good enough. So it will tell us if the model is uncertain about a particular prediction. And we will use this to pick up the correct let's say the most informative candidate, the candidate that might give us the most information for our model, and we do the labeling, retraining, and then we repeat this loop. The result of active learning is depicted here on this picture. So basically on the x-axis, we have the amount of annotated data, whereas on the y, we present the model performance. So if we look at these three different curves that we have here, first let's look at the blue one, which represents the random sampling. So random sampling, we see that the model improves with time, so with the amount of new annotated data, but it does this slowly. However, it is very steady. It means that in time, most probably we will cover the whole data space and we will come up with a stable, reasonably good model, but we need a lot of time. If we use an ideal active learning, we come up with this green curve, and this means that the model will learn faster and it will converge to the similar value than the blue line much faster. So here we see that like with 1/3 of the examples, the model achieved the same accuracy as the blue one. In real life, however, we quite often deal with curves like this, the red one. And it means that in the beginning, our starting point for active learning is not good enough. Either we have picked too little or examples that are concentrated on just a part of the data space, and the model is unable to converge in the beginning as fast as possible. So we have something that in the beginning is worse, but then it converges to a good faster than the random sampling. So usually we are dealing with this. Quite often it also happens that we see that there are no big changes or differences between the random sampling and our active learning strategy. So the whole idea here is that we focus the human on the parts of the data set where their input would give us the most value. So here we have an illustrative example how this works. We will just look at the picture. So on the left-hand side, we see that we have data represented in 2 dimensions, and they represent 2 different classes, the green class and the red class. By the naked eye, we see that roughly the boundary between two classes is here at the 0 value. But we see that there is some noise where these two classes are now overlapping. So the idea is that out of this data, we built a model by selecting as little examples as possible and to have as accurate model as possible. So the first picture here, the middle one, represents the random sampling. So we have taken 30 random instances, we labeled them, and then we built a model out of it. We see that the result is somehow okay-ish, but it does not, it could be improved much more, right? And we see that the selected instances, data instances, they're from all over these two classes. Here we used active learning. The first thing that we see is that the boundary between classes is now much more accurate with the same amount of the data. And we also see that the data that was selected to build this model is much closer to the line. This roughly depends on how the model started. So there is some randomness in there, and then there might be also some randomness in the selection process, but moreover, this converged faster to our, let's say, ideal model. Now we said that there is an issue how we start our active learning loop. So in the beginning, we don't have labeled data and we also don't have the model. So it's kind of a chicken egg problem. But everything starts with the data. So we need to somehow come up with the initial data set, which will give us a reasonably good initial model. So the first strategy, which is not here in this picture, is basically the random strategy. So if we pick enough data instances by random, we can reasonably believe that this will cover majority of our data space and we will come up with a reasonable model. However, there are smarter approaches. The first one is this geometric or unsupervised approach. Unsupervised machine learning approaches are those that do not require human labeling effort. So basically, we take all our data, we put it through an algorithm, which is typically a so-called clustering algorithm, and we will come up with some sort of structure within this data space. So the algorithm will put similar data instances together. So when we do this initial data set selection, it would be very reasonable to pick something from each of these clusters because we believe that these clusters by themselves better represent, let's say, the content of this data space that we have. We do a similar thing with this self-supervised learning, where we use the autoencoder principle of deep learning in order to come up with a more content-wise rich data space. So this rich latent space embedding, which is depicted here in this picture. This is very similar to what we have here with geometric approach, but the latent data space will contain more information that are typically more informative for our machine learning models. So, for example, we might be using pictures. Let's say that we have an algorithm that will try to distinguish whether some material is good or it has some failures. So typically we would use like picture with resolution, for example, 1000 by 1000, which means that it would have 1 million feature on the input end. But if we use an autoencoder, depends on the use case, but we can shrink these million values down to, let's say, 1000 or even less. And these 1000 values will represent this latent data space where we can do then clustering on top of this and come up with better solution. Then another very interesting option nowadays is leveraging the foundation models, like the LLMs. The most simple way to do this would be, for example, in the smart ticketing use case, you use the capability of the LLM to do zero-shot prediction. You put in your ticket and you ask them how this ticket should be classified, and you will get a reasonably good model, which will not be perfect, but it's a very good starting point. The other useful thing that you could use out of foundation model is also their potential to build embeddings, which we use a lot in our approaches. So you already have a model that will give you a good embedding and it will help you to do your selection strategy better. And then the last approach is the so-called transfer learning, which is very difficult to achieve, but it basically means that if I have built a model on a similar use case and I want to put it into another setting, it should be easy to leverage what we have learned before, and we just need to add a small adapter to build this gap into the new domain. Okay, so we have learned in general about active learning, but now we will go through these sampling strategies. So we will go through a series of pictures that look very much like this one on this slide. So basically we start with the big pool of unlabeled data. We have a sampling strategy here. We select a particular instance, we give it to the human oracle, which we label it. We fulfill our data set with the new labeled data, and we build the models, and then we repeat. So with the random sampling, we basically don't care what kind of model we have, and we don't care how it performs on the unlabeled data. We just take a random number generator and pick a particular thing out of this. So this is very cheap and simple to implement, but it takes a lot of, it's very inefficient. It takes a lot of human work to come up with the model. The better approach is to use the so-called uncertainty sampling. So here, instead of the randomness part, here we have these selectors, which are least confidence margin selector and entropy selector. So how do they differ? Each model, when it gives a prediction on the unlabeled data, it will give us the label, which in this case will be either it belongs to class A or belongs to class B, but it will also give us a sort of estimate how certain it is that this instance belongs to a particular class. So this divisor for this estimate is usually 0.5, which means that everything that falls above 0.5 is class A, and everything that falls below is class B in this example. So basically, you would go through all the unlabeled data. You would check which data instance has this measure close to 0.5, and you would take the closest, and then you would give it to the human oracle. This works really well. It is also quite stable and it's simple to implement. On the other hand, you can take one particular class and you can take this estimator of a certainty, and you would check how certain this estimator is for tickets that are positive or they're negative. And you would take two examples from one class and you would see what is the distance between these closest 2 points in one particular class. And then you would check what is the class that has, or what are the instances that have the smallest gap. And then you would take these instances within this gap. So you could also expect here that you do not just take the confidence into account, but also this distance. And this should be better in theory. And you give this. And then we generalize this approach by the entropy. So we don't just take two instances, but we take more. And then we somehow take into account the distribution of these probabilities on the whole class, and then we take the most appropriate candidate. So this is also relatively easy to implement. It's converging better, but it can get stuck in some part of the data space because we are always close to this boundary, which sometimes can be problematic. Then we have committee-based sampling strategy. This is a little bit annoying to implement because the better this strategy will be, the more models you will need. These models will typically be very similar, but they might use different algorithm, different hyperparameters, or they could even use a different part of features from the data instances that we select, like similar, like the random forest methodology approach. So here, typically, you would build like, a large amount of the models. You would train them with your labeled data, and then you would perform these predictions on the unlabeled data set, and then you would look at the disagreement between these committee members. So, and then you would see what is the data instance that these committee members do not agree on, and then you would give this to the human oracle. So yeah, this is annoying to implement, but it also takes a lot of computational time because you need to maintain and run these multiple models. Then we have a sort of orthogonal methodology that can fit different ones that we have mentioned before, and it's so-called the strategy about diversity. We have briefly shown this in the slide about the cold start. So here we don't care so much about the models, but we care that we select diverse data samples out of our pool of data. This can be ineffective when we have more and more instances because there's no additional data than just like the clustering or the latent data space structure, but it's a very good additional strategy, which we show on this side. So basically, you could take this density-based measure and you could combine it with, for example, the entropy-based sampling. So you would have some kind of mixed score where you would, on one hand, use entropy to select the best example, but you would also weigh this with the data that you have already sampled before, and you would need to explore the part of the data space that you didn't explore before. So this is, I think, pretty nice, and it usually improves the accuracy and the convergence of the active learning part. And then comes the last one, which is my favorite strategy. And it's simply because that before, when we were trying to estimate which data instance to label, we were relying on some kind of external, let's say external measure. It was the previous model which gave us the estimate about how sure it is about a certain instance. This is okay, but what we do with the model is basically we try to take a particular data instance and we say, okay, we will choose this one, and then we label it class A or class B. And then once we label it, we retrain the model. And when we retrain the model, we try to observe how much did these models change. So we concretely see what is the effect of labeling a particular data instance on the model itself. So basically, we don't rely on something that was calculated in the previous step. And this is why this approach is, from the efficiency point of view and the budget point of view, it's really effective. But on the other hand, it's really extremely expensive to compute because in this strategy, you would go through all the instances and then you would rebuild for each instance, multiply by number of the classes that you have, you would rebuild this model. And this can take a lot of effort. Okay, here is a comparative analysis of all of these strategies that we were just discussing. I will just leave this for information here, but we will not go into details of this slide. And now I would like to show you a little bit how active learning works in practice. Okay, so I will reload this app. You can also open this by yourself. Here is the URL, and also on the slide you have the QR code before. So we will compare here directly how entropy-based active learning is compared to random selection learning. Basically, we want to build a model here that will distinguish between color green and color blue. It is, of course, subjective, and it will be based on my perception of colors. But here we see the examples that the model is offering us. Here we have ability to label this data. Here we have some data about the accuracy of the model and the model weights, as well as here. So basically, we are putting logistic regression on top of this data space, and here this is depicted. So basically, the ideal model would be the one that would have intersection between this gray line in here. Everything that belongs on this part will be color green, and it is a negative class in this example, and everything that falls here will be blue. So we see that these two models differ already in the beginning. This is simply because of the randomness, because I randomly initiated this cluster. So we see here that entropy model is already better here. Also, the curve here better corresponds to what we see, what we want to get in the end. So if I reload, we see that this changes and the starting points can be different. So let's say I will start from this one. So the entropy-based model will ask me first about blue. I will label this blue. Then it gives me the complete opposite. I will label this green. And again, I want green. Okay, this was now too much. Blue. Okay, and now I see that this curve is now somewhere where the intersection is close to the real intersection that it needed. And now the entropy-based selection is not giving me extreme colors anymore, but it gives me colors that are closer to this boundary here. So this is still green. Now the boundary moved. So now this is blue. This, let's say this is green. This is blue, green, blue. I don't know, maybe green, but for sure blue. So we see that we have converged now to a pretty close to the ideal model. We also see that this curve is pretty nice, but we see that we alternate now for the sake of imbalanced classes. But after 14 iterations, we are very close. When we are dealing with random, sometimes the model will converge faster. Maybe here it even will. We will see what happens, but in general, it doesn't. So it asked me for blue. It was already very much biased towards the blue side. Now again, it gave me the blue. So model is actually getting worse. Now randomly it popped in some green. The model is improving, but now it's again blue, blue, green, green. Okay, now we see that the model is now in the space where it could have some impact, but because it randomly selects the numbers, it again gave me blue, which will make the model worse and still worse. Now this is green. Okay, so I will just play with this for a little while. We see that even now, when we are in the late stages, the model will still give me the colors that it can clearly identify as blue. But through time, this model slowly but very reliantly will close the border. But you see that I need a lot of more effort to use this. Okay. So you can also scan the QR code here. Okay. And now I would just like to show you that in order to label less data, you don't always have to use active learning. You can also be smart about it. So here we have some industrial demo, let's say, where we want to classify the surfaces of a particular material, and those surfaces can be normal, like in these three labels here, or they can have some issues like cracked, scratches, or stains on it. So to approach this, traditionally you would build a convolutional neural network, which is depicted here, and you would try to fill in as much data as possible to make it as good as possible. This is again the learning curve for active learning approach. The blue one uses entropy and the red one uses random sampling. We see that there is almost no difference between one another, and we also see that the learning curve is really, really slow. So we have labeled here almost 600 examples, but the accuracy is still below 0.8 or 0.7 or 0.6, depends which curve you are looking at, whereas the baseline here is a little bit more than 0.9. On the other hand, if I'm a bit smarter, I can already with 50 labels examples get a result that is very close to the baseline. Why? So here we are training the convolutional neural network. It has a lot of parameters, but instead of doing this, I could just extract an embedding out of the picture and reduce the dimensionality of the problem significantly, and then just use a traditional model. I think here I used gradient boosting, and within 50 examples labeled, I was already in a very good, here with a very good accuracy. Okay, so this is just a reminder that it's worth to think a little bit about the issue that you are dealing with. Okay, just to conclude this fast, I will show you some selected use cases from the HumAIne project. The first one is the one that you will see later in a demo. It's the smart finance use case or smart ticketing use case. So here we have help desk tickets, and we try to build a model that will dispatch them to the team that needs to be done. So before that, we were talking about embeddings in the data space. So these embeddings are here done with the sentence transformers and these HDB scan methods. And we see when we depict this in 2 dimensions that we see nice clusters where we can see what these clusters are all about. So about install writes needed, about Java update, VPN client, and so on and so forth. So this would already be, for example, a good start to build the initial data set. So anyway, this is our system. So the ticket itself has some other features, has a description, and it has a title. Title and description are sent through the sentence transformance to generate an embedding, and the other features are one-hot encoding is used so that we get the features that can be used for machine learning. We get encoded data, which basically means that here we have feature vectors. We do the split to the train and test set, and we use the train set in our active learning loop in order to improve the model. So the results are depicted here. You should look at this picture so that you compare all other lines to this blue one. The blue one represents random sampling. And we see that majority of active learning approaches behave better than active sample because earlier they give us a better result. If we, for example, compare here the red line and the blue line, they achieve the same accuracy, for example, 0.77 around here. For this, we needed like 25 examples. For the random, we needed more than 80 examples. So it's really much more efficient to use active learning in this case. We also calculated something that we called acceleration. So how much faster can we achieve the same accuracy of the model by using active learning compared to the random sampling? And we see that this is drastically above 1. And on average, this is in the end of our training process is about 2.3 and 2.4 for two different use cases, which means that you need almost more than 2 times of less of the labeling to come up with the same models. We also have a use case for generating first reply. So user inputs in a ticket, and then our goal is to generate the first reply. We do this by implementing the technology that I mentioned before, but also we use the retrieval augmented generation system, which I will not go into details about it. The most important thing about human in the loop is this part here, where we basically use human feedback in order to improve this system. So what we do is we take an input ticket, so something the user has set. We try to find something similar in our database, and if we find it, we use those samples in order to generate next answers. And then the user itself has the ability to either upvote or downvote a particular example that our system has chosen, and we use these statistics in order to make these selections better in the future. Because we are a little bit late, I will skip this example. I will just show you. So we also deal with oncology. There we are dealing with interpretation of radiological results, which is in a text form like it looks here. But for the medical system, we want to find certain things in this text and put them in the tabular part. So this is also something that we are trying to solve with active learning. So to improve the model as fast with as little work by the doctors as possible. And we also have a different human in the loop use case, which is related to smart energy. So here we are trying to find stability of the grid in Greece, the electricity grid with 1 day ahead assessment. And for this, we use another model. It's a process model, and it's very computationally expensive. So active learning itself does not query human for the labels, but it queries a model. So here we reduce the computational cost that we have, but we have in this loop a human operator, which is basically guiding in which direction this system should explore our space. So just to conclude here, active learning is a very well-defined methodology in the machine learning. It has been very popular even before the year 2000. But nowadays, when we talk about active learning, we have in mind more about how human is then included into this loop of training a machine learning model or an AI system, and then many different approaches become very interesting to explore and research. Just the last slide. So we have built a HumAIne Active Learning framework. You can get it on GitHub. Basically, this framework is exposing an API which you can use to build new active learning models or go through the training of these models or get info or save this model, and finally also to use these models. We also include some explainable AI and other things which you will see in the demos later. So this concludes the first part of our presentations. Thank you.
Thank you, Clevin, for the wonderful overview of the component.
This is our
for the sake
application that we're gonna showcase today, the smart ticketing demonstration. So this will be focused on the integration of the active learning and the usage of the active learning linked to a ticketing app that will manage and support users that need to manage tickets. So in this case, we'll be able to see how explainable AI and benchmarking elements are integrated in the system to see how the user will be aided during this kind of process. Michele, if you can, okay, yeah. Thanks. So yes, as I was saying, the tool will cover mostly AI-assisted ticket classification. So the system will be able to detect automatically starting from a model pre-trained or not trained already, and from the model being able to effectively recognize tickets and help the user to label them and sort them in a faster way. In this process, we also have human in the loop oversight. So this means that the user is always able to see what the machine is doing at all times, and is able to interact, change, or fix any kind of behavior that is not compliant with what it's supposed to be. And this provides a constant feedback, as we were saying before, for the machine to learn and adjust the parameters while still being operational. All of this is also looped in with the explainable aspect of it. So it's less of a dark black box, but we can see the reasoning, how we got certain results out of the machine and understanding the process that went into it. And finally, we have the active learning and benchmarking that both, especially the benchmarking, provide a sight into the status of the machine, and not only the machine, but also the user that will end up using the application. So we can see how effective the system is actually is. The app has a loading anonymized tickets, and as from this we can, in the current model that we have, we're using tickets that can that are loaded and we can manage by ourselves, but not connected to anything yet, but eventually will be. So we're basically simulating real conditions with the AI, and the user will create will use a model or create and train a model that will be able to propose classifications per ticket, and depending on the current setting of the application, will be able to be auto solved basically with just minimal input from the user, or can fully be controlled with manual control and then AI aid basically. So yes, as I was saying before, this will show how we try to integrate the concept that we explained before, and how we wanted to have an application that was able to display the real human AI collaboration flow, and it will also demonstrate the readiness of WPP3 and 4 technology, and prepare evaluation for M29 and M36 testing. Also, with the benchmarking, we are able to have transparent monitoring of the tool, as it enables the user to see the exact process that is going on. And explainable AI also brings in this level of transparency. So the user interface and the architecture is pretty minimal, as you will see, but it doesn't mean that the process is not big behind it. We try to keep it as simple as possible, so the user can have a clear picture of what's going on at all times. But still, even though it can be simple looking, it doesn't mean that the power behind it is not present. So as I was saying before, as we operate to the app, the AI is always gathering information. So this will make the backend more powerful as it keeps being used, even when it's being trained or when it's just being used, so that we can have a precise system behind it that will just keep on learning and managing better the information and have a better effect for the user. We use anonymized data, of course, to keep the security and privacy of the data that we're being passed by, as also not to poison the data well, basically. And we try to keep it as clean as possible. The visualization from the human in the loop interface is can be viewed at all time as we bring a page that will allow the user to have always an eye for what's going on and how the data is being managed and how it impacts the AI as we're using it. So we are having logs that are both present in the front end application, but also on the back end application, that can make better understand how the AI is calculating and managing the tickets. And we show this as a conceptual integration of explainable AI. The data that we use, though, are all based on historical data and come from real examples and real life situation and contexts. And here we have the demo of the current application. So as we can see, we have the main page that tries to help the user to start up the process, starting from a new model. And here we choose a random model as for the demo. We're able to load any kind of data that we want, and we also can change the model and the data savings system. So that, as we can see, we entered already the training phase of the model. So as we can see, we have tickets that have not been labeled yet. The AI right now is able to infer the use of these tickets, but it's still too imprecise. So it's recommended at first to have some training first and then start actually the process, even though it's still possible to try and use it even with no manual training, as the application, as said before, learns by itself, learns on its own with continuous integration. So as we can see here, we are labeling tickets just to give it a little head start, basically. We have direct feedback of what went on. So a labeling process and sorry, and the score it got. And we saw how if we kept going at it, we could have seen how the AI would have been better each iteration. So right here, we have already the first example of dispatching. So the user will have a ticket that will come up, and the AI will try to infer or deduct the grouping of the ticket, so that it can be dispatched to the proper team properly. And here the user can decide whether on accept the prediction or reroute the ticket manually. We also have the prediction and why we got that prediction. So the explainable AI part that I was talking about before. And we can see how certain words highlighted and the reason that went behind the solution we got, also showing past tickets. We have a manual showcase of inputting a ticket coming from completely the user, so it can be completely manual, and still the AI will manage to find the correct solution. This is purely for having a manual control over ticket management. We have a classification and both suggested response that will allow the user to have a better approach to the ticket, and it will show how and why we had that response based on past tickets that it solved. The inference applies the same logic to the ticket resolution. Sorry. With more efficiency and more data showcasing the current use of the model. And this also brings in the active learning aspect to it. We got precise details about the tickets, the similarity to other tickets, or the usage of analogous examples. And finally, we have the analytics. So as I was saying, the benchmarking suite that is taking currently, keep gathering data and seeing how the AI keeps on learning, and what also, not only the AI, but also the human and the AI are both working to solve the issue. So yes, this was our project. Simple enough. If you got any question, I'll be happy to answer them.
All right. Thank you. Thank you very much, Filippo, for the overview of the use case.
As also anticipated by my colleagues, the smart ticketing pilot actually have a few very strong points, which is of course speed and efficiency that the human and automation, hybrid human automation process can bring to the management of incidents, accidents, and whatever requests of any kind. The quality and control that is brought about by the fusion of an automation and a human constantly in the loop approach, especially also for complex use cases, which is of course performing better than the completely automation, and also powered by explainable AI modules by design, which gives a strong layer of trust and transparency to the whole system, and also the active learning itself that actually pushes for continuous improvement within the whole systems, and also so helps also getting better and better in the whole overall ticketing system. This, in our opinion, enables what can be called controlled automation, which is, of course, better than pure automation, which is something that has been applied also in the past or to other use cases also similar in this, and which has been seen to be faulty many times. So this is the core improvement is the human in the loop itself, and at the center of the whole process. And moving on to the ticketing process as a field of analysis. We believe that the ticket can be intended as a universal operating pattern. Here you can see actually the ticketing process and all its stages, which are actually very, very replicable in many different fields, such as the operations fields, customer care, compliance, and each is an underlying pattern that is very much industry agnostic and can be applied to many organizations for many different projects and many different contexts. The only thing that will be changing, of course, will be the systems of the company slash the organizations, the data that need to be provided, the different procedures and governance rules, which can all be mapped in the same type of process, of course. And here is just a few very prominent, in our opinion, other potential use cases that can follow a similar logic to the smart ticketing one to provide a AI-driven with human in the loop solutions, which is, for example, retail and e-commerce use case in the management of orders, customer support, payments, and any kind of accidents that can be also related to payments, transactions, orders, and so on and so forth. And also in manufacturing concerning the production, downtime, the shop floor, maintenance and incident handling, the whole application, the whole also ticketing process concerning these manufacturing domains, and also all the others systems and services that are also embedded within organizations. So let's think about, for example, HR, also operations within big companies and corporates, and also across its clients, their clients. So all these processes basically follow a similar pattern to the application maintenance and ticketing process, and all of these can actually improve with a system similar to the one deployed for smart ticketing, which is explainable and transparent by design, so powered by explainable AI, able to improve itself thanks to the active learning and the benchmarking suite, and also it puts the human at the center and in the loop for quality and control, and to improve what the pure automation can actually do on itself. So that's basically it. And this concludes also our GFT presentations for the smart ticketing pilot. Thank you, everyone.
Thank you very much, Roberto.